Thank you for that wonderful introduction. And Vice Chancellor and SLU, this is truly a tremendous honor for me, and I really appreciate that. I decided to talk about something that has not been published. It's new research. And I did that partly because of the wonderful data that Sweden has in terms of the national monitoring system. You are an envy of the world, and we use your data in many ways, and I wanted to share with you some of our more modest attempts to monitor in Canada. So, deciphering the effects of climate change in the north. And in Canada's north, there are very few people and very little monitoring that has been done. Yet these changes in atmospheric and terrestrial systems can result in very disruptive forces acting on aquatic systems. Often these changes are slow, but they seem to be coming more faster as a result of anthropogenic climate change. In this talk, I want to present data done by myself and my students that the lakes in the north are approaching a tipping point towards fast and probably permanent changes in response to climate change. My focus today is on phytoplankton. Phytoplankton are the microorganisms that are at the base of many aquatic food webs. Now, phytoplankton are very important for providing energy to lakes, but they also produce some of the most harmful natural toxins known to science. In particular, cyanobacteria, which is one type of phytoplankton, has been linked to an upsurge in neurological disorders that include things like Lou Gehrig's disease, Parkinson's, and even Alzheimer's disease. This photo here is taken of Lake Erie, and you can see the wonderful phytoplankton bloom on the shores near Ohio. In 2014, this bloom resulted in a closing down of water supplies for the city of Toledo, Ohio. So here you can imagine being situated on one of the wonderful Great Lakes of the planet, but unable to drink the water because it had toxins, and in this case it was a microcystin toxin. Now, this is happening around the latitude of the Great Lakes, but there's great concern that this is starting to move northward. And a common prediction is that climate change will enhance the phytoplankton biomass and potentially the toxins in these northern lakes. And of course, there are many vulnerable people living in the north. In Canada, many indigenous communities living in the north that don't have the luxury of water treatment, and so are on the front lines of these types of climate changes. Why is this a common prediction? Well, in the north, we see among the highest rates of climate warming. In the pink line, you'll see what it is, the warming over time for the Arctic, but just below that, you see the rates for Europe and North America. So we're seeing amongst the highest rates of warming in these northern latitudes. But it's not just about temperature. We're also seeing high rates of what is called hydrologic intensification in the north. And basically that refers to wet areas becoming wetter and dry areas becoming drier. So we're disrupting the hydrologic cycle as a result of climate change. Now this is my depiction of the carbon cycle. And what we know is that soils and vegetation are major carbon sinks for atmospheric carbon, and that very little of this carbon actually moves towards fresh waters. But as a result of the climate warming and the hydrologic intensification, we're seeing a disruption of the soil carbon and a greater release of dissolved organic matter, and in that includes dissolved organic carbon, nitrogen, and phosphorus to fresh waters. What we see are these changes of warmer and higher precipitation, resulting in greater export of dissolved organic matter to lakes. And this is called a browning of the lakes. And some of Chris Berg, who's a Swedish scientist, is one who published a lot about the lake browning or the brownification of northern lakes. And what we see is not only an increase of dissolved organic matter, but the character is changing. It's becoming more humic, more aromatic, it's larger, it's heavier, and it absorbs more ultraviolet radiation. Now clearly, all of this will have consequences on the lakes. The lakes will absorb more light. The UV will penetrate to a shallower depth. you have greater thermal stability and a larger nutrient pool. And guess what? Phytoplankton, and in particular cyanobacteria, thrive in those types of conditions. What we predict is that we'll have an increase of total biomass of lakes up to a point, and you see it's like a little bubble and then it drops down, because the dissolved organic matter, first of all, fertilizes the lakes, but eventually light will not be able to penetrate and it becomes light limited and the biomass will decline. We'll also see a reduction in essential fatty acids potentially, and that means that the quality of the food may deteriorate. And we predict that the cyanobacteria toxin production will increase as the total biomass production also increases. So these were our theories, and this work was actually initiated in Abisko, Sweden, where we had a workshop of people around the world who gathered, and some of the best minds predicting what the effect would be of climate change on lake browning and the consequences. So now we wanted to see if any of these kind of hypotheses were actually coming true. So here we turn to citizen science. And again, remember, in Canada, our north is data poor. And we have to rely on some of the local citizens living on some of these lakes to tell us what's happening to the lakes. In this time series that you see from 1994 to 2017, it's the number of reports of citizens saying we have an algal bloom in our lake. And when they report that, the government then goes and tests the water and determines what's in that lake. And what you see is that the increase of reports went up, and in those reports, cyanobacteria is the dominant phytoplankton. And again, cyanobacteria with a risk of those toxins that could cause neurological disorders. But the question is, you see that beautiful image of Lake Erie with the phytoplankton bloom, and that's in the media, and everyone's looking at that. Is this really an increase, or is it just people becoming more aware and looking for it? And so how do we know if this is due to global changes or if it's simply due to an increased awareness in society? So this is where our monitoring efforts came in. To determine if climate change is enhancing phytoplankton biomass in lakes, we started with a collection of 10,000, actually it was 12,463 lakes, in an intact northern forested landscape. We didn't want to have it interfered with things like residential areas, agriculture. We wanted to get a clean signal from climate change in this northern landscape. Now, phytoplankton biomass data were obtained through modeling of chlorophyll A, which is a pigment in the phytoplankton, using Landsat imagery over an almost 30-year record. The best part is, in a data-poor area of a large country, is that this imagery is free. And it just takes a small army of students to work up the data in order to extract the chlorophyll from it. We were quite ambitious. We wanted to map the world. We started with North America. We soon realized that very few places have data where the satellites coincide with chlorophyll A measurements. Again, what you have in Sweden is pretty special. So we ended up using our networks, finding data wherever we could, and started to map the chlorophyll A over the time series in these various regions from the polar down to the tropics. So Landsat detects basically the reflectance of water in the blue, green, red wavelengths, as well as the near infrared. But what I show you there in this picture here is the green is the chlorophyll A, but we have other constituents in the water that could mess around with that signal. And in particular is that dissolved organic matter. That browning color can interfere with the chlorophyll. So we started looking at a whole series of different algorithms and different models, including linear, exponential, logarithmic, and power. And we took that over the entire range of different geographies that we looked at to come up with what was the best algorithm for detecting chlorophyll, but not for detecting the brown of the water. And so what we found was blue minus red over green worked really well. We could predict almost 80% accuracy of the chlorophyll in the waters, and we knew that that was not interfered with the browning signal. So we then applied our model to our intact northern landscape, and we focused on the temperate forest biome of the Great Lakes Basin. And this is what our data showed. So again, these are the median chlorophyll 30-year time series. And what you see is what I would call a chaotic distribution of data. There are some that are what are called hypereutrophic, very high levels of chlorophyll scattered throughout, but equally there are some that remain highly nutrient poor or oligotrophic. And when we look at these maps of the distribution, I tried really hard, but I couldn't see a logical pattern for explaining where would we find ones that are eutrophic and again at risk of those cyanobacteria blooms. So we then decided to do some really simple statistical analysis. This is what we call a two-way analysis of variance. And basically imagine taking the 30 years of images and all the lakes in there, and you want to collapse it into basically what can be explained over time and what can be explained over space. And what we found under space is that 17.4% of the variance in chlorophyll had a spatial component, and I want to focus on that first. So basically, 17.4% of the total variation in phytoplankton biomass was covered in a spatial dimension. The trophic status of the lakes ranged from very nutrient poor or oligotrophic to hypereutrophic, but we wanted to know what controls the median chlorophyll. And so we go back to the catchment. And I'm a watershed scientist or a catchment scientist, and I have to go back to where are the nutrients coming that would subsidize the lakes that could then cause these algal blooms. So we looked at hypothesized controls, which included the climate, temperature, and precipitation. But we also looked at the catchments and the distribution of wetlands within them, because the wetlands are sources of nutrients and the dissolved organic matter that the chlorophyll and the phytoplankton can utilize. We also looked at what we call the ecotones, that area in between the deep water lake and the catchment. We call it the littoral zone. And the idea is that the wider that littoral zone, the more nutrient loading could happen to the lakes. And then we looked at the lakes themselves, and we wanted to look at their nutrient dilution potential, which was based on the volume of the lake. But we also looked at the nutrient resuspension potential, which was how easy was it for nutrients locked up in the sediments to come back up into the water column. So these were our hypothesized controls, and we went through and did a lot of digital terrain analysis and used some of these state-of-the-art techniques. And this is a complicated figure, but I'm going to walk through it very quickly and easily with you. From the bottom left to right is basically the concentration of chlorophyll. We have very low levels on the left and very high levels towards the right. When we look at the first determining factor for high levels of chlorophyll, they were the smaller lakes and they were the warmer lakes. One of the ongoing theories globally is that algal blooms like it hot. And basically this shows that in this case, the smaller lakes were the ones that were warmer, were the ones that produced the bloom. But that's only a small proportion of the lakes. Let's look at the whole left-hand side. And what we found was that larger volume lakes that were wetter, with lower resuspension from the lake bottom and lower loading from the land to lake, remained oligotrophic. And the ones in the middle are those that had something in between, that you started to get greater resuspension from the bottom or loading from the littoral zone. So we have a very complicated situation here. The ones on the right are basically the early warning ones of temperature only, but everything else is much more complicated. Now, we wanted to look at the temporal domain. And this was, to me, somewhat surprising. Only 8.6% of the lakes, that's over 12,000 lakes, showed any trend. So we wanted to first understand what controls it. So we first looked at the distribution of them over the landscape. And this was the real surprise. We thought that 8.4%, that they all would be getting more eutrophic. But we found that 4% of the lakes were becoming more eutrophic, and 4.4% were actually becoming more oligotrophic. And we couldn't figure out why. So we have two different directions happening in response to climate change in this region. But what was even more surprising was that 91.6% showed no change at all. Now, I'm a scientist, I'm sitting there going, that doesn't make any sense. What could I be missing? And so again, turning to some of the more sophisticated statistical analysis and theories, we go back to Sheffer and basically lake stability concepts. And basically, when you look at stability, you have something where you have an increasing pressure, in this case it's climate change, and you're maintained in that stable state for a period of time. So in this case, most lakes on that landscape are oligotrophic. They're stable there, and no matter how much climate change is happening, they're still stable until they reach a transition point. In that case, they're going to shift from being nutrient poor and start to become eutrophying. And then they're going to be in an unstable state. This is that tipping point. Am I going to become eutrophic? And if I become eutrophic, that's going to be pretty hard to reverse that trend once you go over that hump. Other lakes are stable, but what we found is that some of them might actually be going the opposite way. So with that kind of theory, we had to figure out what statistical tools can we do to kind of see if the lakes were maybe not showing trends, but were showing some instabilities. And so we worked on something called spectral anomaly analysis, and basically, again, a more complicated figure, but I'm going to summarize it for you simply. You have a chlorophyll A time series, you remove the trends, you remove the naturally occurring oscillations, and you look at the residuals. And the magic is in the residuals. Now, many of us as scientists look at outliers. And when I was early in my career, we always wanted to find a reason to eliminate those outliers. I'm here to tell you to embrace the outlier. Because when you embrace the outlier, a detective will find signals. And so what we looked at were those residuals, and we started to look at the time series of the residuals. And what we found here is that if the residuals were increasing, then the system was eutrophying. If the residuals were decreasing, then they were oligotrophying. Similarly, if they remained high throughout, they were unstable. And if they were low throughout, they were either stable eutrophic or oligotrophic, depending upon what the chlorophyll A concentration was. So I'm going to show you something in a very more simple way. This is the same results with the chlorophyll on the y-axis. And basically, we analyzed those 10,000 lakes and found over 5,000 of them to be stable and oligotrophic. We only found 146 to be stable and eutrophic. We found 1,500 to be switching back and forth. Remember, those are the ones that are teeter-tottering and not sure what their future will be. And these are the ones, this subset of 2,600 lakes, that we started to see what we originally thought was going to happen across the board of lakes that are becoming more eutrophic. And again, this was the surprise. We have an almost equal number that are going in the opposite direction. So to summarize this point, I think it's to show that when you look at simple statistical analyses like trends, I only found 8.4% of the variance could be explained. But when you look at statistics that allow you to look at the stability analysis, I found 56.6% of the lakes were showing instability, a much larger number. So what is driving the lakes to potential tipping points? Again, we used regression trees. And in this case, we wanted to know what was driving the changes in phytoplankton biomass, so we only looked at those that were oligotrophying or eutrophying. And again, high rate of drying, so if you have low precipitation and warmer temperatures, those are the ones that are starting to create those algal blooms. But on the right-hand side, you see those with a higher rate of wetting or slower rate of drying and a smaller volume. And this one I had to think about what could that relate to in terms of a nutrient supply. I thought it could be shorter water and nutrient residence times, and therefore the phytoplankton can't take up the nutrients, and therefore they remain very low. And in between, you see that as you increase the residence time, that you're starting to get more of the eutrophic lakes. So to conclude, climate change is leading to a disruption in the phytoplankton of these northern lakes, but the responses are quite complex. However, the risks to society are significant because as these lakes have the potential of going over a tipping point into a new reality, it's going to be really hard to reverse them, and the risks of having these toxins produced, as well as other changes like hypoxia and other things that would affect the food supplies in these lakes, are real and of concern. Thank you.